All right, so this is the second course this semester for BC1, and it's called Equilibrium Chemistry, or Equilibria, and it follows on directly from what you've just had, thermodynamics. And Equilibria really starts to think about, okay, well, we can think about the energetics of chemical reactions, but let's think about them in movement. So when chemical reactions are proceeding, what's driving them, but also what do those factors that drive them mean? And all that's a little bit abstract at the moment, but hopefully it'll become clear in a second. And this is especially important in biological chemistry because there's a kind of a saying that equilibrium means death. In other words, if the system is at equilibrium, you know from thermodynamics that delta G is equal to 0. That idea, delta G is equal to 0, means the system has no capacity to do any more work. So if it's no capacity to do any more work, it's not going to do anything. It's just going to sit there, and in biological terms, that means death. So as we'll see throughout this course, or certainly in the first 3 lectures, in biological systems, things keep changing so as to distort the system away from equilibrium so that it has to try and make this drive towards equilibrium again. So very clever things happen to change things like concentrations or pressures or anything that will just give the system a jolt so then it has to try and work its way back towards equilibrium. So this is how all energy processes in the body are driven forward. Okay, so the book is the standard chemistry textbook that you have for all of these courses, and there's a whole chapter in equilibrium, so most of what I talk about will be based in that chapter. There's a couple of things, a couple of extra things, for example, in the next lecture, that are a little bit beyond that book, so I'll give some references as we go. But pretty much everything should be self-contained, either in the lecture notes or in the textbook, so you shouldn't, unless you're interested, you shouldn't need to expand your reading beyond that. Right. So the way I try and work is that on Learn there are gap notes, which are essentially completed notes apart from any questions I ask, so you're able to look at those. So this system here is one we'll discuss a little bit more in the next lecture. I'll mention at the end of this lecture, but this is the classic situation where equilibrium chemistry comes into play. So we have a system where oxygen from the air needs to get into body tissue. And the process by which this happens is a couple of different jolts, essentially, to systems, so a couple of different chemical reactions that are either influenced or disinfluenced by surrounding factors, and those factors will affect equilibrium. But we have a reaction here that, in very simplistic terms, is hemoglobin, which is this enormous system here, will bind to 4 oxygens. So hemoglobin has 4, each hemoglobin system has 4 iron sites that oxygen molecules can bind onto. So in the lungs, oxygen binds onto the hemoglobin in the bloodstream, and then it passes through the bloodstream and then is released where necessary in the cells. And we'll talk a little bit about why this process is favourable. We write this as a forward-reverse reaction because both of these processes are feasible depending on the conditions that we look at. So rather than just a simple chemical reaction where we have A plus B going to C, we have the reverse as possible. C can go back to A plus B. So this is less likely in, for example, the combustion of methane. If we think of methane plus oxygen goes to carbon dioxide and water, it's very unlikely if we take carbon dioxide and water that it's going to form methane and oxygen. So we don't really think of those kind of reactions as equilibrium reactions. They tend to go to what we call completion, where they tend to just completely go in the forward direction. Okay, so in very simple terms, which I'm sure you know from school, we have a chemical reaction where reactants react to form products, and if the reverse is true, and the reverse is always true, but the extent to which it is true is the principle. In other words, where the products that we form can go back and form the reactants. This gives what we call an equilibrium reaction. So instead of using this one-sided arrow, we use this double-headed arrow here with the arrowheads being halved. Okay, so half forward arrow, half reverse arrow. Okay, so that gives an equilibrium reaction where reactants will go and form products. So obviously we have reactants forming to go to form products, products breaking up to return to reactants. So there are two reactions going on here at the same time. And as I mentioned, this is I mean, it's a really interesting chemistry, but it's fundamental to biological chemistry. Things like I mentioned, hemoglobin binding, which is a sort of a special case of docking, or protein ligand binding equilibrium. So we'll discuss these in a little bit more detail in the next lecture. But this idea of being able to quantify the extent to which these processes happen, that's all based in equilibrium. All right, so what we can say is that if we had our simple system, okay, or even our complex system, hemoglobin plus oxygen, obviously as our reactants react, so if I start here, if I use the, so if we have our reactants here, okay, so before the reaction starts, obviously we have a certain concentration of reactants, assuming no products have formed. That's not always the case, but let's assume at the start that no products have formed. Obviously, as the reaction proceeds, that concentration is going to decrease. And in normal circumstances, for example, combustion of methane, that would decrease until the concentration of methane decreases to zero. All of the methane that we would combust would go and form carbon dioxide. It would be very unlikely that any methane would remain. So we would expect in that case that the concentration of our reactants would keep decreasing until their concentration was zero, and the reaction would finish, it would end. So that's not the case here. We're seeing that the reaction levels off after a certain time. Why does it level off after a certain time? There are several reasons why. We'll discuss some of them. But essentially, we see that the slope of this graph, okay, if I take a straight line at any point here on this graph, we see that it's decreasing over time. Now, you'll do kinetics in a while, in a couple of lecture series, I think. But as we have, at the start, when we have lots and lots of reactants, the possibility of collision, or the probability of collision, is very high. So it's very likely that reactants will collide and form products. Okay, so for a reaction to proceed, reactants have to collide with enough energy to overcome the activation energy barrier, okay, to break apart those initial bonds so that they can form new bonds, and then go and form products. So there's an energy barrier associated with reaction. So that comes from reaction collision. As more and more reactants are used up, so as the reaction proceeds, more and more reactants are used up, the probability of those reactants colliding reduces because there's less reactants. So as we have lower concentration of reactants, the probability of reactants colliding is less, so therefore what we call the rate of reaction is slower. So we see this concentration time graph getting less and less over time because the concentrations of reactants are decreasing, so therefore the probability of reaction is decreasing. And it reaches a point where it begins to level off. Similarly, obviously, as we begin to form products, the concentration of products will increase over time, and they level off, obviously, at exactly the same point as in the simple reaction as the reactants. Okay, so this, I hope, is blindingly obvious, but it's really just saying that we can start to map out now on this graph, different points. We can say that as the reactions form products, their concentrations decrease as the rate as well as the rate of decrease. Okay, and this rate thing is something we'll come back to. Obviously, the concentration of products increases, and then we're going to reach a stage where the concentrations of both reactants and products stay the same. And this is what we call equilibrium. Okay, we reach a stage where the concentrations of the system don't change. So we have a system, we have a human body or a reaction vessel or an ocean or whatever our system happens to be, and we're looking at the concentrations in that system and they're not changing. That does not mean, and we'll come back to this again and again, that does not mean that the reactions aren't continuing. It just means that the forward reactions are happening at the same rate as the back reactions. So A and D are reacting to form products at the same rate as C and D are breaking apart to go and form reactants. So at this point of equilibrium, the forward and back reaction are still occurring. Okay, so equilibrium doesn't mean everything just stops. The system isn't just sitting there doing nothing, but the rates are the same. So it's essentially, if we imagine lots of people running out of this lecture theatre and lots of people running into this lecture theatre. If I was to count the number of people in this theatre at any time, if the number of people running out and the number of people running in are the same, well, there's always the same number of people in this theatre. All right? So that doesn't mean there's no movement in this theatre. It means that from my point of view, there's always the same number in here. So because the rates are the same, we don't observe any overall change. Okay, so this rate is the rate of reaction. How fast is the reaction proceeding? So that means we can define equilibrium concentrations. Concentrations at this point where the system concentrations aren't changing, and they'll remain unchanged as long as the system is left undisturbed. Now, when I teach chemists, that's where we leave it because we're happy. System's undisturbed, everything's great. Let's take the concentrations and go on and do some thermodynamics. The problem is in biology, the system's constantly changing. Everything constantly changing. Pressure's changing, pH is changing, concentrations are changing. Things are constantly changing. So we don't have this system where it just goes on very nice straight lines forever. The body just keeps coming in and doing something else, doing something different to perturb the system, so then it tries to restore back to equilibrium again. Okay. So because we have this movement, we call this dynamic equilibrium. Okay, the dynamic is really just trying to emphasize that molecules aren't just sitting there. Reactants are constantly forming, products are constantly breaking apart back to reactants, but the two are happening at the same rate. So we have the teddy bear analogy on the treadmill, where the treadmill motor is going at a certain speed in one direction, teddy is running at the same speed in the other direction. So from our view on the side, he's not moving, but obviously he is because he's running against the track. All right. Okay, so then we can start to say, well, what does that mean in terms of extent of change? So in my simple analogy here, I just drew this coming down a certain amount and this coming up a certain amount. But obviously, the more reactants that to form products before equilibrium is reached, the more likely we're going to have what's called a product-favoured reaction. In other words, here we have a reaction where the reactants react quite a lot. Okay, a large proportion of reactants react before we start to reach equilibrium concentrations. So this is what we would call a product-favoured reaction. And here, thankfully for us living on Earth, this is what we call a reactant-favoured reaction. It is very unlikely that nitrogen and oxygen that is in this room at the moment will form nitrogen monoxide. So therefore, this reaction does not go very far before it reaches equilibrium concentrations. Only tiny, minuscule proportions of nitrogen monoxide are in this room at any point, and usually they've been formed by some catalytic process, such as car engines. So this is what we would call a product-favoured equilibrium, where the concentration of products are greater than the concentration of reactants. A reactant-favoured equilibrium is where the concentrations of reactants are greater than the concentration of products. Okay, so we can use the idea of these ratios of concentrations to give a sense of where does this reaction lie. Excuse me. And that's then obviously the equilibrium constant. So the equilibrium constant is given by the symbol is used the symbol K. So this is basically the ratio of products to reactants. So we have the concentration of products divided by the concentration of reactants, each raised to the power that they appeared in the equation. So here we have C moles of product C, so it's C to the power of C. All right, so you've seen that in school. One slight, now we're not going to go into this in too much detail. One slight problem is this is a little bit of a lie. All right, we don't really mean concentrations here. We mean something called activities. And activities are a chemical term meaning how much of a particular concentration is active in solution. So if I say I have 100 molecules of a substance in solution, but perhaps several of them are clustered around each other, so the ones in the middle aren't actually doing what we say they're doing in the chemical reaction, well then the activity of that solution is going to be just a little bit less. So when we talk about concentrations, we're simplifying. We're assuming it's dilute solutions. We're assuming it's what's called an ideal solution. And for reasons I'm not going to go into, but it's in more advanced physical chemistry textbooks if you want to, that means when we work that through, because of the way activities units work, that means that K, the equilibrium constant, will never have units associated with it. Okay? Now, many textbooks are wrong in this, but we should not associate any units with the equilibrium constant K, regardless of whether there's 2 products upstairs and 1 product downstairs, or 3 products downstairs and 1 product upstairs. It doesn't matter. K does not have units associated with it. Okay. So, do you want to try a question? Very easy to start off and see how you get on. Okay, so this should be very easy. All right, so this should be something when you answer when you were in GCSE or equivalent. So we've got the equilibrium constant K is equal to the constant. Oh, this should work. That doesn't work. Right there. So the equilibrium constant K is equal to concentration of products, NH3 squared to the power over the concentration of reactants cubed. When you shove all those in, I get 664. Okay, so we've got ammonia here is 0.34 molar squared divided by 185 times 0.098. Okay, 664. No units. All right. So no units here. Now, in the old days, of course, I used to be able to mark students down in exam papers for putting in units, but now you'll just be offered the option 664. Okay, but a couple of things I want to dwell on here. Let's say, and obviously this is not the case, so let's say here there was some other substance formed and it was a liquid, and maybe there's a solid here, some other substance as a solid. Why don't we include those in the equilibrium expression? Well, strictly speaking, it comes back to this idea of activity. Okay, and we say that the activity of solids and liquids are one. In other words, that they don't contribute anything to the overall equilibrium change. So we don't include anything that has a liquid or a solid symbol in our equilibrium expression, only gases and aqueous concentrations. All right, so if we had a liquid here or a solid, we wouldn't include those in our expression. And you probably remember this from things like ions, salts forming ions. So this is the Ca2 plus, which was aqueous, plus 2Cl minus, aqueous. So here the equilibrium expression for this, which is given a very special name called the solubility product, in other words, how soluble is this species, will be equal to the concentration of products, concentration of our ions, divided by the concentration of reactants. Well, we don't include the reactants here because it's a solid. Solid has an activity of 1, so we don't include it, okay? Another way of thinking of it in more simple terms is that the concentrations of solids and liquids is so vast compared to the concentrations of gases and ions in solution, or species in solution. And in terms of equilibrium, we're thinking about change. So if those concentrations are so high, the extent to which they change is very small. So therefore, we only consider the species that are dilute. That's a bit of a weaker explanation. So that's why we need to move on to activities. You will never be asked anything about activities. I'm just trying to say to you that there's a lot of hidden myths about equilibrium in terms of units and in terms of why we do and don't include things. And to really understand those, we need to mention this term called activities. All right, so the equilibrium constant is equal to the concentration of products to their power divided by concentration of reactants to their power, so 664. So as I said, we can use K to get a sense of the position of equilibrium. So here we have a K value that's tiny, 10 to the minus 31. All right, so that means the top line here is 10 to the minus 31 times effectively smaller than the bottom line, or the ratio is 10 to the minus 31. Here we have the other extreme, hydrogen and oxygen. If we took hydrogen and oxygen together and put a spark there, it's unlikely that there will be any hydrogen and oxygen left behind. Okay, it's pretty much all going to form water. So that has a very high equilibrium constant. And then we have an intermediary zone between, say, about 10 to the minus 5 to 10 to the power plus 5. They're sort of numbers that are feasible, indicating a kind of there'll be a balance of reactants and products. So here we have hydrogen and iodine. This will form an equilibrium. There will be appreciable concentrations, measurable concentrations of both products and reactants here that we could go in and sample, work out what those concentrations are, and work out an equilibrium constant. All right, so when you see very, very large numbers or very, very small numbers, that means it's effectively a one-way arrow. It's when we have these intermediary numbers, that's when we're talking about equilibrium. All right, so more important for you guys is not when things level off, okay, so not down here when we are, when we achieved equilibrium, but what happens beforehand, okay? Because in biological systems, it's all about, well, what parameters have changed or what conditions are pushing towards a particular equilibrium. So very often we don't want to sample here, we want to sample much earlier. We want to find out what's going on at this stage. But the problem is if we sample and then sample 2 minutes later, the concentrations will have completely changed. There won't be equilibrium concentrations. The great thing about equilibrium is if we sample here, or sample here, or sample here, the concentrations, because the equilibrium concentrations haven't changed. So we can say whatever we like about that system at equilibrium. But if we want to know what's going on before equilibrium, we need a different way to think about it. So before we reach this leveling off point, we have pre-equilibrium, and obviously the concentrations of products and reactants are changing at that point, so we can't call these equilibrium concentrations. So instead we talk about the reaction quotient Q, it used to be called more commonly the mass action ratio. This is the same definition, but now the only thing that's different is that when we put in these concentrations here, C, D, A, and B, these are not equilibrium concentrations, okay? So when we talked about the equilibrium constant K, even though we didn't mean it, really we should have put a little subscript EQ beside all of those concentrations to emphasize that they are equilibrium concentrations. So the only difference between K and Q is that K, the concentrations are equilibrium concentrations. For Q, the concentrations are any concentration. They may be equilibrium concentrations, in that case, Q is equal to K. So where is the reaction at? Is it pre-equilibrium? Is it post-equilibrium? Is it at equilibrium? Can we get a sense of where the reaction is going? Okay, so you can try this one. So here we have the glucose 6-phosphate, fructose 6-phosphate system. And this is sampled, okay, so this is the isomerization that happens as part of glycolysis. This is sampled at a particular point and gives these concentrations. And if we know that there's a couple of things to unpack here. If we know that the equilibrium constant here is 0.43, all right, so this is our equilibrium, very simple equilibrium, that has this equilibrium constant. We always quote an equilibrium constant at a temperature because it's temperature dependent. So we sample the reaction at some stage. So we go in sample and we find that it has at that point these concentrations. So we want to know what is the reaction quotient Q, and then by comparing that reaction quotient Q to the equilibrium constant, we want to know what's going to happen to the system. Is it going to go in the forward direction? Is it going to move at all? Is it going to go in the reverse direction? How do we know that? We can find that by determining, by relating it to Q. Okay, if you think about what the definition of Q is. So I'll let you work on that for a minute before we go on. Okay, so the calculation itself should be fairly straightforward. So hopefully that. Okay. So we've got our equilibrium is. I was gardening at the weekend. Oh dear. Right. So our equilibrium is G6P fructose. Okay. So obviously the reaction quotient Q will be the concentration of products, which is fructose 0.02 over the concentration of reactants 0.08. So 0.02 divided by 0.08 is 0.25, so that's the easy part. So it's either A or B. Obviously, these are sample exam questions, just in case that isn't clear. So that's easy. So it's 0.25. So which way is the reaction going to go? Which way? Reverse. Forward. Okay, so if the equilibrium is 0.43, isn't it? So our K value is 0.43. So this system will keep driving until K is equal to 0.43. Its sole reason for existence is to get to 0.43. But the only way it can get to 0.43 is to, if it's currently at 0.25, it has to obviously increase. Okay, Q needs to increase, so Q is less than K. So to increase Q, either the top line has to increase or the bottom line has to decrease, or in reality, both in parallel. But the top line has to increase. That means the concentrations of products must increase. So this reaction is going to be proceed in the forward direction. All right, so we can use this idea of Q to get a sense of where is the reaction at. Is it close to K? Is it very far away from K? Is it past K? Is it before K? Okay. Okay. So obviously in this situation, it's in our simple example of where we have the concentrations of. So we will be sampled it here. So Q is equal to 0.25, whereas we know that the concentration of reactants needs to keep decreasing until we get K is equal to 0.43. We could have disturbed the system some other way. So we could have, for example, shoved in a lot of extra products. So the sample could have been doped with fructose, and that would have pushed the concentration of products too high, so therefore Q value would have been greater than K, and the system would have reacted by going back to the reactants. Okay, so if Q is less than K, the reaction will proceed in the forward direction. If Q is greater than K, it will proceed in the reverse direction, and if it's equal to K, well then the system's at equilibrium. Okay. Does that make sense? So Q is basically a very handy measure for looking at where our system's at relative to equilibrium. Right. So to finish up this introduction, we'll just talk a little bit about disturbing equilibrium, because this is where biology especially makes things interesting. And it's a little bit erroneous to call it this, but it's commonly called the Chatelier's principle. And this says that when a chemical system is at equilibrium is disturbed, the system will do whatever it can to return to the equilibrium position. So it will do whatever it can to counteract the change that was imposed on it to return to where it was. So if you imagine the system energetically is at the bottom of a well, okay, so our equilibrium means our system, delta G is equal to 0, so the system has no capacity to do any work. Energetically it's at the bottom of this well, and something comes in and just pushes it out of the bottom of that well. The system will do whatever it can to return back to the bottom of the well. And in other language, we are the system's at equilibrium, so K, our Q value is equal to K. If we disturb it in some way, we are now changing either the concentrations or the conditions of the system so that Q is now no longer equal to K. So again, we're back to our setup where Q will determine whether the reaction needs to go in the forward or reverse direction. So if we had our system before where we add in some reagent, so if we had our sample glucose to fructose, and excuse me, if we have equilibrium concentrations such as these, we can easily calculate K. So if we calculate K, it'll be 0.03 divided by 0.07, which hopefully gives us the 0.43 we had on the previous slide. And then we change it. we've changed it so that we double the concentration of glucose 6-phosphate. So what you want to do is work out what Q will be as a result of that, and then what will happen to equilibrium. Okay, now you can do this in two ways. You shouldn't need to work out the value of Q. But what we're doing here is increasing the concentration of reactants. So how will the system try and accommodate this change? Okay, so that conceptual idea should marry up with the calculation you do. All right, so what you need to do here is calculate a new value of Q based on the new concentrations. Okay, so we have the concentration of glucose is 0.14, fructose is 0.03. Calculate Q and then explain how the equilibrium will shift. This is the last calculation. Okay, so the numbers should be fairly straightforward, but the reasoning may be a little bit less so. So, just to make sure, we have glucose 6-phosphate going to fructose 6-phosphate. Okay, and we knew that at equilibrium the concentrations were, what happened here? 0.07 and 0.03. The equilibrium concentrations are 0.07 and 0.03. So that means the ratio of these two will be in that ratio at equilibrium. So now we've come in and we've doubled the concentration we've chucked in a load of glucose in here, so we've doubled its concentration to 0.14. So what would happen to the system to offset that change? Yeah, it'll move in the forward direction. We had our equilibrium setup where the concentration of reactants here was slightly higher than the concentration of products. So if we increase the concentration of reactants, well, some of those are going to react to form products so that we return this ratio. Both sides will be higher, but the ratio of the two will be the same. So if we increase the concentration of reactants, it's going to drive the reaction forward, so we should see an increase in the concentration of products. So increasing the concentration of one side, the system will move away from that side to try and rebalance the ratio between the two. Then we do the sums, well, we get Q is equal to concentration of 0.03 divided by 0.14, which is 0.21, is it? So 0.21 for a K value of 0.43, well, Q will need to increase to achieve equilibrium, so therefore the reaction will be driven in the forward direction. Okay, so it's easy to work out conceptually, but we can also use this idea of Q to work it out in terms of numbers. So we can say that Q is equal to 0.21, and since this is less than K, the equilibrium will shift towards products. But what's happening here is the equilibrium is changing to offset the change that we imposed on it, according to Le Chatelier. All right, so changing concentration is one very powerful way the body uses, pH mainly. Changing acid concentration is a very powerful way that the body uses to drive equilibrium. And the second half of this course, the last 3 lectures, are all about acid-base equilibrium. Okay, changing pressure. So I'm sure you know from school that the system will restore to the least number of gas molecules. If we increase the pressure, we will have so if we have a system where we have oh, come on. I was thinking about it. No. Oh, I pressed the wrong one. So we have, it's N2 plus 3H2 going to 2NH3. Okay, so we've got 4 gases on one side and 2 on the other. If we increase the pressure of this system, what will happen? The system will try and reduce the pressure. Okay, it will try and reduce the pressure by occupying a lower volume. a lower volume means a smaller number of gas molecules. So if we reduce the pressure, the system will shift, sorry, if we increase the pressure, the system will shift to the lower number of gas molecules, so that it reduces the overall pressure of the system, because the smaller the number of gas molecules, the smaller the pressure. All right. And here we have two gas molecules going to two gas molecules, so there'll be very little change on pressure in the system. If we change the pressure, it's going to change the equilibrium very little, perhaps just very slightly towards the right, because they're the same gas molecule. And this is back to our hemoglobin example. So if we look at hemoglobin, why does it at one stage take up and in another stage release oxygen so readily? So it takes up oxygen in the lungs. Okay, so when we inhale, we're inhaling oxygen into our lungs, and hemoglobin in the bloodstream is ready to bind onto any oxygen that's present. So if we look at this equilibrium in terms of pressure alone, we've got 4 gas molecules on one side and no gas molecules on the other. So in very high pressure situations, the system is going to shift towards products. So in our lungs, when we inhale, we've got a much higher pressure system, about 14 kilopascals, so the system will shift towards the least number of gas molecules to reduce the volume and hence the pressure. So the system is driving this reaction forward, driving oxygen binding onto the iron in hemoglobin. And then it transports it through the blood into body tissue, where the pressure is much lower, and the system shifts to a larger number of gas molecules. In other words, it's freer to expand to a larger number of gas molecules and releases oxygen to wherever is needed. Hemoglobin is much more complicated than that. We'll talk a bit about that more in the next lecture, but that's the pressure aspect of it, this idea of driving forward the reaction in the lungs especially to get oxygen to bind onto the iron and hemoglobin. Okay, and then finally a change in temperature. So change in temperature means the system will shift to offset that change. So if we have a reaction that is exothermic, a reaction that is giving off heat, and we increase the temperature of that reaction, what will happen to it? It will shift towards what will happen to it? So if we have a reaction that's giving off heat and we increase the temperature, how will the system offset that change? Move to the reactant side, because the reverse reaction is, if the forward reaction is exothermic, the reverse reaction is endothermic. So if we have a reaction that's exothermic and we increase the temperature, then it'll disfavor that reaction moving forward, and it'll move in the reverse direction. Okay, so if we increase our temperature here, the system will counteract it by going in the reverse direction. And the synthesis of ammonia is the classic example of equilibrium for 20th century chemistry, because of course the synthesis of ammonia, or what's called the fixation of nitrogen, was the Haber-Bosch process. So this has allowed us to essentially pluck nitrogen from the air and bring it into something tangible that we can bring into essentially food, the nitrogen source of food. So Haber, Fritz Haber was the German chemist, a German Jew, who was a brilliant scientist, and his understanding of the equilibrium chemistry of ammonia led to this. The problem with synthesis of ammonia is it needs to be a certain temperature to overcome the activation energy. But if you increase it, the temperature too much, the system will be pushed in the reverse direction. So we needed an increase in temperature to get the system to go at all, to overcome the barrier, but too high, and it would favour the reactants. So they brought in the idea of pressure, and using pressure to drive this reaction forward. And this has essentially led to the population explosion of the 20th century. This allowed, for example, fertilizers to be developed and so on. If you're interested, Haber is a particularly interesting character, just as we're coming up to the 75th anniversary of the Holocaust, because he, of course, was also then recruited by the Nazis to manufacture things like Zyklon B, which were used in the gas chambers, including on his own family. And so he is one of these very controversial characters in the history of science. So if you're interested, it's a very good Radiolab podcast on Fritz Haber, which discusses a lot of equilibrium chemistry. But this balance between thinking about reactants and products, thinking about temperature and pressure, is one of the kind of interesting ways of exploring equilibrium and how we can use equilibrium to change chemical reactions. So next time, this is really just sort of an introductory, make sure everybody is up to the same bar from school level. Next time we'll talk a little bit more about biochemical processes, hemoglobin and protein ligand binding, and then we'll go into some more calculations and phys chem about equilibrium in the third lecture.